So what we're going to look at here is a horizontal Atwood machine. And I've got a frictionless cart, low friction cart, with some mass bars stacked on top of it, 4 to be exact. So multiply 5 total objects, each with a mass of 250 grams, and you get a total mass of 1.25 kilograms. And then that string goes over this low friction pulley, and the other end of the string is attached to a few masses which have a mass of 125 grams or 0.125 kilograms. So the mass of that cart over there is 10 times the mass of this hanger right here. So to represent that schematically, I've got a picture up there on the Jumbotron. So what we're going to do is we're going to connect the smart cart to the Capstone program. So over here I've got Capstone pulled up. And the first thing we're going to do is look at the velocity versus time graph. So over here right now I got this set to record velocity. And we're going to look at the velocity time graph and see if we can just measure the acceleration of this thing. And then we're going to switch it to a force versus time graph, because that string is connected to a force sensor, to see if we can get an idea of what the tension in that string does. And so let me see if I can set this where y'all can see my cart and possibly even the data on the screen. Go gadget tripod work. There we go. Somewhat. Okay. At least you know I'm not switching things on you. So I'm going to press record on the Capstone program. I'm going to move this thing right here. I'm going to let it accelerate down the track. And I'm going to catch it hopefully, before those masses hit the ground, so that I don't do any damage to my stuff. So let's hit record on my mouse. There it goes. All right, so it's recording now. Velocity versus time. I'm going to hold it back. Let it go. Okay, there we go. So what you noticed, coming over here to our velocity time graph, is the velocity starts off at 0. So that's me just kind of wiggling it as I pull that mass out of in front of it. It goes up relatively steeply to some really big maximum value, and then it sharply comes back down to 0. It even goes below 0. Here's 0. So that's when I caught it, and then I pulled it back just a little bit as I caught it. And then here's where I click stop. So the points that we're interested in are when it's speeding up. So from about 5.5 seconds to a little more than 6.5 seconds. So that accelerated for a little bit more than 1 second. So to get the acceleration from a velocity time graph, I'm going to select just that portion of the graph. So draw my box around there, kind of get a little bit more of it. And then I'm going to do that linear fit. So I'm going to choose linear over here. Okay, and so coming in on that box, my linear best fit tells me I have a slope of 0.836. And again, the slope of a velocity time graph is the acceleration. So 0.836 is my acceleration. So I'm just going to record that over here on my whiteboard. So A experimental 0.836 meters per second squared. So we'll compare that to the theoretical value that we get using Newton's laws to predict the acceleration of this thing given that ratio of masses. So the next thing that I would like to look at with y'all is the force. So I'm going to go back to the Capstone program, and I'm going to change this from a velocity graph to a graph of force versus time. And let me get rid of that linear fit real quick. So this one looks kind of crazy, but all this craziness over here at the end was when I caught it. So what I'm going to do is I'm going to zoom in a little bit. Remember that it accelerated from about 5.5 seconds. So there's 5.5 seconds. You notice there's this little drop off to about 6.5 seconds. So what we're going to do is after that little spike right there, I'm just going to kind of cut it off. So here's what was actually happening during the time that it was accelerating. So you'll notice that with the exception of this little wiggle right here, this is when I move that mass out of the way and I move the cart back just a little bit. When I was holding it at rest, it was one constant value of about 1.2 I gotta stop doing these when the bells are about to ring. About 1.2 newtons. And then when I let it go, at just after 5.5 seconds, the tension drops. And it drops significantly by about 0.25 newtons. So almost like a fifth of the weight was missing when I let go of that thing. And so in order to understand why that is, we shouldn't focus on this thing, but instead we should focus on that thing. So let me back this up real quick and let's focus on this thing. Right now, the forces on that thing are in equilibrium, meaning that the tension in the string has to be equal to the weight going down. When I let it go and it accelerates downwards, now the forces on it are unbalanced. And so if it's going to accelerate downward, that means that the gravitational force is going to get larger than the tension force. Well, the gravitational force doesn't change, so that must mean that the tension force is decreasing. And so when I let it go and that thing accelerates downwards, that means that the tension is decreasing throughout the string, which is exactly what we're seeing right here. Here, that little hanger is in equilibrium. Here, it's accelerating downward. So the upward tension force was smaller than when it was at equilibrium. So to get an exact value for that, I can, again, select just that part. A little box there. Select just the part after I let it go. Do the statistics tools, and here I want the average. So I'm going to choose mean. From there. Okay, so over here it's got my average for me. So the tension in that string was 1.08 newtons. So over here, write T experimental equals 1.08 newtons. Okay, so that's what we got for our experimental results. Let's now compare those to the theoretical results that we calculated earlier. And for that, I'll turn you over to your teacher in present time. Until next time, ta-ta.